Welcome back, guys. Now I'm going to carry on with the same, it's basically the same subject as in paper and pen, but now we're going to use some slides just to understand, just to have like a big picture. At the beginning, in the paper and pen version of this video, I was talking to you guys that at the end, we wish to find the classification function f, which produces the smallest as possible expected risk in terms of every other function g inside my bias, my algorithm bias, okay? So some of the steps over here I mentioned before, so I'll make it shorter, but you guys have access to the slides just to read those and discuss and ask questions later, okay? Here we have the expected risk being shown. We have a loss function L computed in terms of every possible input and its expected output, and the result of my classifier or classification function f being applied over x, okay? And this is an expected value in terms of my loss function. Of course, this is not computable if I don't have access to my joint probability distribution. So at the end of the day, I have the empirical risk as a possibility to be computed because I have access to some n sample size, n size sample, a sample size with n instances, which have, of course, the input variables, the expected output, and of course I can apply my classification function on top of those inputs to have some result, some output, and to verify, of course, if it's equal or how far it is from the expected result. And this is, of course, an average, okay, as I mentioned before. So I cannot compute this, but I can compute this, because this depends on a sample. This depends on the whole joint probability distribution. Assume the joint probability distribution is formed by a space in which every attribute in my input space is a real number. If it's a real number, how could I represent every possibility for real numbers? It's just impossible, and compute the loss in terms of that. Of course, it would be impossible, but at the end of the day, I can compute for a sample. Okay, that's quite interesting. So instead of finding the minimal value for the expected risk, because it's not computable, I can do it for the empirical risk, but there is a problem when I do this for the empirical risk we discussed before. The problem is if my space of admissible functions contains an f, a classifier, a classification algorithm, classification function, which is a memory-based function. If it's a memory-based function, using my sample, I can find a given classifier that's going to reduce this as close as possible to 0. And of course, it's going to be equals 0, because it's going to memorize my training sample. But what happens when I receive more instances? It's going to miserably fail. Okay, we're going to discuss that, of course. So before, remember again, we discussed about the law of large numbers. Vapnik just observed that he could take advantage of the law of large numbers. What is the law of large numbers? An average of a given variable, which I have access to the realizations of that variable, approaches its expected value as the sample size of this variable tends to infinity. Of course, this requires some stuff. First of all, this function, which is an average, wasn't selected in terms of my data, wasn't biased in terms of my data. I didn't look at my data previously and said, okay, I'm going to select the average because the average is going to be the function that probably, for instance, is going to over-represent some characteristic I have in my data. That's not the case with the average. The average is kind of agnostic to my data, okay? So it doesn't depend on my data. It's just a function, just the average. And here I have its counterpart, which is the expected value. Another point, every sample I collect for this variable has to be an independent and identically collected instance from my joint probability distribution. It cannot be selected from a given region of my data distribution and then I carry on selecting from the same region. I have to give the probability, the possibility of selecting any possible value of my joint probability distribution. Okay. Another point is that this it is only valid if my data distribution is fixed. If my joint probability distribution does not change over time. If it's the same, for example, okay, it's a Gaussian function with this average and this standard deviation. So it's going to be the same all over. It's not going to change, okay? Another important stuff, Vapnik just came up with the idea, okay, so I could get the empirical risk and study how it approaches the expected value of this loss function. If it's a good estimation of my expected value for this loss function, I can use it to select the best as possible model, the best as possible classifier, the best as possible classification function. When I say model or classifier or classification function over here, it means the same. And that, of course, when my sample size tends to infinity. When I talk about this, when something tends to infinity, I'm talking about convergence, uniform convergence to be more precise, okay? So this is a result that was available for Vapnik before. This is the law of large numbers with the upper bound defined by the Chernoff concentration inequality, which is over here. This assumes that every value of this variable is in this interval 0, 1, belongs to this interval, okay? If it doesn't belong, it's not going to work. Here, I think we could discuss something. I could show you guys like some nice example. Let's open. I'm going to increase the font over here. Yeah, like this. And I'm going to open my R and I will simply plot this upper bound term. 2 times the exponential of -2 times n times some epsilon to the square. But of course, it's not going to work because I have to define my sample size. Let's say my sample size grows from 1 to 1000. Okay, this is a sequence simply, okay, from 1 to 1000. A vector from 1 to 1000. Of course, it's not going to work because I need to define some epsilon. Let's say I accept over here an epsilon equals to 0.01. So the greatest divergence I accept in between my estimation and its expected value is going to be epsilon equals to, this is the same as 1%, as you guys may notice, because everything over here is in interval 0, 1. When I plot this, take a look at my plot, I can understand how the convergence happens. Oof, it's not converging yet, because my y-axis is greater than 1, and it cannot be greater than 1, because this is a probability. So I should increase my sample size to something like 10,000. When I plot now, it's converging, but it's still like, it's not close to 0. Let's increase this to 20,000. And plot again. It's going to converge to 0. What do I have over here with 20,000 observations? I have the sample size that ensures that such a divergence in between my estimation and my expected risk to be greater than 0.01 is upper bounded over here by the last value of this. What's the last value of that? Take a look. Let's see over here. It's this. It's 0.03. That basically means that in 96.33% of the scenarios, my estimation is going to be as close as possible, and this is the possible, okay, epsilon, to my expected risk. And this possible in my case is 0.01. If I come up with a different epsilon, I'm going to change it over here. If I define epsilon as 10% and I plot it with, let's say, in red, what's going to happen is that I need much less observations. I don't need like as many observations as in here. Of course, if I change this to 5%, take a look. Oops, in green. If I change this to, for example, 2%, let's plot it in blue. Take a look. The smaller my divergence epsilon is, the more instances, the more examples I need to ensure that my average is going to approximate my expected value. It makes sense. I need more instances to be more precise, and this is like a precision, as you guys may notice. Okay, so going back now, here what Vapnik did was exactly this. Oh, I want to use my empirical risk over here as an average, and here I want to use my expected risk. That's what he did, but there is a problem over here. Remember, I cannot select this function based on data, because if I select this doesn't work. This is only valid if I take an agnostic function, a function that does not depend on data. And when I talk about machine learning, I'm going to adapt my classifier in terms of my data. So if I adapt it in terms of data, it's going to be dependent on my data. So I cannot simply use it like this. Of course, if I just select out of the blue a function f from my algorithm bias, this works. But if I select something based on the learning stages, the learning iterations of my algorithm, this is not going to work. Okay, let's go on. Of course, there's a bunch of things over here I explained before. It's not necessary to explain again, but you guys will have access to all those slides to get back and understand what's happening over here. Okay? So, at the end of the day, what Vapnik was worried was exactly this. He decided, instead of selecting just one function and representing the law of large numbers for a single function, he decided to represent for every function we have in a given space of divisible functions, aka bias, algorithm bias, which is our uppercase f over here. Consider this axis has all functions like f1, f2, f3, f4, f4, and so on. Doesn't matter. The worst case is, what is the greatest divergence we have in between the expected and the empirical risk? Assume over here we have some expected risk, and over here we have some empirical risk. Here we have a divergence. Here we have this difference, this absolute difference. If we see the expected and the empirical curves over here, they work as curves, as functions. When I compute the difference, the maximal difference in between a pair of curves, I cannot use the max over here, max operator. I have to use the supremum. The supremum is the same as the maximum for scalars, but supremum for functions. Okay? So when I compute the maximal divergence in between two functions, this is the supremum. What is f belonging to this uppercase f? This uppercase f is this space over here in which we have all those functions, and the greatest divergence over here is the one we are interested in. Basically, I'm interested in the worst case scenario. When I say I'm interested in the greatest divergence, given my space of admissible functions, I worry about the worst case. The case in which I have the greatest divergence. Of course, when I increase my bias, as I mentioned before in the previous classes, of course I have a higher probability of having a memory-based classifier inside my bias. And that's going to provide the greatest divergence to me, because my error in my training sample is going to be 0, but my expected error is going to be very, very large. Again, risk and error is the same, okay? Just a different name for the same stuff. Okay. Over here we have what Vapnik did. So he came up with this formulation. He came up, okay, I want to have if I just select a given function f inside my bias, my algorithm bias over here, I can say that this is the divergence. But what's the worst case? The worst case is always going to be greater than or equal to this guy over here. Of course, this guy for a single function is going to be smaller than or equal to the supreme. When it is equal, when the same function, let's say here we have a function k to be selected, and here this function is function k just by chance, so it's going to be equal. But let's say here it's function 1 and here is function k. So function k, let's say function k represents the worst case scenario, so it's going to be greater. Okay, that's why we have this smaller than or equal. Of course, when I apply probability on both sides over here, what I will have is the representation we have here. Okay, so I have the probability of this being greater than epsilon and the probability of the worst case scenario being greater than epsilon. In that particular formulation, we are worried, of course, Vapnik was worried about finding the solution for the worst case scenario. Why the worst case scenario? Why? Again, the law of large numbers cannot be used if I don't specify a function, if I don't define which is going to be the function. If I have the whole bias of an algorithm, which is going to be the function? Could be any function inside the bias. When I get the worst case scenario, I am specifying the function, and I'm not specifying it in terms of my data, but I am specifying it in terms of my bias, in terms of all functions, in terms of every function my bias can represent, in terms of every function my bias makes available to my algorithm to learn from data. Okay? That's quite important. Okay. Here we're going to take a look at some stuff. I think this is interesting. Just consider this is the expected risk of the best classifier I have in my space of admissible functions uppercase f. And this is a first function I started with. So this is the same as saying, okay, this is the expected risk for any function inside my bias. Let's say this is going to be, for example, the first function my algorithm, my learning algorithm starts operating on. So it's the first function it's going to adapt in attempt to find the best function ever inside my bias. So this difference is of course greater than or equal to 0. Why? Because this expected risk is going to be greater than this expected risk over here. This has the smallest as possible expected risk. You know which is the best function inside my bias is the one that best approximates my joint probability distribution. So its expected risk is going to be as low as possible given my bias. So, of course, it doesn't matter this absolute value. Why I can represent like this? Simply because my expected risk for any function inside my bias is always going to be greater than the expected risk for the best function inside my bias. It's going to make less mistakes, the best function inside my bias. That's why this is going to be positive. So Vapnik just made like some tricks over here. You guys are gonna see. He took this. Okay, I start with a given function inside my bias, and I want to find the best function inside my bias. So he decided to sum up and subtract the empirical risk of this function, which is any function inside my bias, and summed the same empirical risk over here, and subtracted the empirical risk of the best and summed the empirical risk of the best. Of course, this cancels out with this, and this cancels out with this, and we have this again. Take a look at this. Vapnik took advantage of this to formulate an upper bound. Take a look at this upper bound. Here we have the same as here as before, but here he found this quite naive, I would say, upper bound. Why this is a naive upper bound? Take a look why it is a naive upper bound. Because when I measure the divergence, the difference of the empirical risk of my function, which is a function I'm just starting with, minus the empirical risk of the best function ever, the best function I have in my space of divisible functions, this difference is always going to be smaller than or equal to 0. Why that's the case? That's just a definition. Of course, if I am adapting my classification function in terms of my data, my risk in my training sample for that function that's being over-biased, over-fitted, let's speak like that, in terms of my data, is going to be smaller than or equal to the empirical risk of the best ever in my space. This basically means that if I over-bias my classifier in terms of my data, of my training sample, this is going to be smaller than this empirical risk. And over here, you guys have something quite interesting as an upper bound over here. Take a look. Here I have the expected risk of f of n minus the empirical risk of f of n plus the empirical risk of f minus expected risk of f of f. This is the same as, take a look, a supremum and another supremum. So he came up with this formulation. So if I want to express all the work, all the effort that takes to start with a given classifier inside my bias and go for the best as possible classifier inside my bias, that's the same as 2 times, actually smaller than or equal, 2 times the worst case. That's the worst case scenario came from here. Take a look. This is the origin of the worst case. This is the origin of the supremum I mentioned before. The supremum I mentioned to you guys in the paper and pen based videos, and also before in this same class. This is the origin of the worst case. Okay? Quite interesting. So that was a way that Vapnik came up with the worst case representation. Again, as this is a 2 times the supremum of this side, of course, if this is going to be greater than a given epsilon, this is going to be greater than a given epsilon, but here I have 2 times the supremum, so I just divide this side by 2 and divide epsilon by 2, and I have this uppercase supremum. This is quite interesting. This is a good step. Here, we can start using the law of large numbers. Why? Because now we have just selected the worst case scenario for the whole space of divisible functions, aka bias, aka algorithm bias. So I'm not working with a function that is over-biased towards my data, that depends on my data, but I'm just selecting the worst case scenario for my algorithm, from my algorithm bias. This is very, very nice. This is so fantastic, actually. So, going to the next step, Okay, now we can start working with the law of large numbers. I'm just going ahead because we know what's happening now, because I just talked to you guys in the paper and pen based videos about this. Here we have again the law of large numbers, and now we can formulate, of course, for every single function inside the bias. Take a look. This is not the worst case anymore. This is a function, a given function, f1 or f2 or f3. I can measure this difference. And for every function, I do have this upper bound. So for the worst case, what I'm going to have? For the worst case, I will have either the first function being greater than epsilon, or the second, or the third, or the fourth, or the nth function, considering we have a finite number of functions inside my bias, okay? Just consider a finite number of functions. Of course, if I can select one of those functions, any one of those functions, this is the same as the probability of selecting the first, or the second, or the third, or the nth function. And that is upper bound by the sum of those probabilities. This is so interesting. Okay, I explained that before in the paper and pen based videos. So let's go again to the next step. So this is an upper bound for the supremum we had here. Just going back, again, the supremum is equal to this. And as this is an upper bound for this is an upper bound for the supremum. And here we rewrote that. This is an upper bound for an upper bound for this. And of course, if I have a sum of each probability, I have a sum on the right side also. On the right side of the Chernoff's inequality too. Okay? Quite interesting again. So from this, we have the very first result, and then, as I mentioned before in the paper and pen based videos, now my dog's barking, but no problem. We have here the use of the symmetrization lemma. Vapnik rewrote this into this. Okay, instead of representing expected risk and empirical risk, because we have no way of computing the expected risk in a given real world problem, because you don't have access to the joint probability distribution, he decided to rewrite in terms of two empirical risks. One in a sample, one in another ghost sample, or in a second sample, so to speak. Okay, and he found out this result. I'm not worried about this, about proving this for you guys. I'm going to share with you a document, a PDF file explaining that. That's enough for now. I'm just going to give a next step, which is much more important for us. You know what's interesting? We're going to discuss now how this, let's give, just go a little further. Yeah, a little further, and then I will come back. Going back, maybe easier. So if I come back over here, I'm going to remind you guys about something. This M over here tells me that I have a finite number of functions inside my bias. But what is this number of functions? What is this constant? Is it a constant? Actually, Vapnik observed that this is not a constant. This is actually a function of my sample size. This is referred to as the shattering coefficient. So we are going to discuss about the shattering coefficient now. I'm going to go ahead, a little bit ahead, and we are going to talk about that. He decided to rename that M of n as meth call n, meth call f, comma n. This is the same as m, okay? This is our shattering coefficient. What is the shattering coefficient? The shattering coefficient is basically a function that's going to represent, I'm going to go directly to what is important, This shattering coefficient is a function that I just substituted over here. And take a look. As I mentioned, the paper and pen base classes, I'm here representing not in terms of the expected risk and an empirical risk, but two different empirical risks given two samples, a first sample and a second sample. When I consider two samples, I have to use this symmetrization lemma, and of course my shattering coefficient is not going to be in terms of a single sample, but in terms of two samples with the same sizes, with the same size n, okay? In this case over here. Just remember what we did in the paper and pen based classes. So this is in place of m. Again, I did that in the paper and pen, in paper and pen videos. I just substituted the shattering coefficient by some polynomial function. Here I just decided, okay, this is going to be 2n powered 2k. If I come up with this function to represent my bias, I'm just saying that my space of admissible functions, aka algorithm bias, grows in terms of my sample size using this polynomial. I can plug this inside my exponential by applying log, exponential and log to this term, and I can sum up both of course powers in terms of my exponential basis, and this is going to be the same as k times the log of 2n minus this term over here. You know what's interesting over here? Here I have a negative term that's linear, and here a log of n. Which term is going to be more important, the positive or the negative? Independently on my k, of course, if my k is infinite, it's just impossible. But if my k is defined as an integer, for example, this negative number, this negative term over here is going to dominate my process. And if it takes over, I'm going to approximate 0 with this exponential. And by approximating 0, what's going to happen is that this upper bound is going to approach 0. By approaching 0, I will have the probability that my empirical risks are going to be as close as possible given some epsilon. Or even better, that my empirical risk, if we go back, is going to be close to my expected risk, the risk I will have in a future sample that I have no idea how. I don't have access to this sample. This is quite interesting, so I can measure how my classifier, my classification function is going to behave over unseen examples, unseen instances, how it's going to behave for unseen data. That's possible if I have a polynomial shattering coefficient. What happens if my shattering coefficient is something like 2 powered to 2n? If it's something like this, it behaves as an exponential function. This means that my shattering coefficient grows as my sample size grows, and it grows indefinitely. Take a look. When I apply the log and the exponential with the log over here, I will have the 2 times exponential of 2n multiplied by log of 2. Here I just put this in evidence to make like n, okay? I have n here and n over here, of course. So I have n times 2 times log of 2 minus epsilon to the square over 4. My problem is epsilon is always a very small number. I want it to be small. And log of 2 is 0.6 roughly. So this is going to be like 2 times 0.6. That's the same as 1.2. 1.2 minus something that's quite small, powered to 2, that's going to become even smaller, and divided by 4, even smaller. Of course, this is going to be an exponential of a positive number, and this is going to grow indefinitely to positive infinite. how could I have some upper bound if this grows to infinity? I'll never have a probability, a bounded probability over here, because this is going to grow indefinitely. You know what's interesting about that? What is interesting is that basically if I have an algorithm bias whose algorithm, if I have a classification algorithm whose bias is so complex that it's capable of representing every function in the universe, what's going to happen at the end is that I will overfit. Why I will overfit? Because I'll never have an upper bound from my probability over here. Let's see that. Okay, you better see. I mean, sometimes people say, but we don't believe. So let's verify. So I'm going to plot those over here. Again, opening R. Let's say I have something like a sample size that grows from 1 to, could be 100,000. And here, let's define my shattering coefficient. Number 1 is going to be n power to 2. And the second is going to be something like 2 powered to n. Oof. Oh, sorry, this is the first. This is the second shattering coefficient. Okay? Now I'm going to plot to you guys 2 times shattering coefficient 1 times the exponential of minus n. Let's select a given epsilon, could be any epsilon. Let's use like 10% power to 2 divided by 4. I have some curve. Oh, this is the curve. It's a nice curve. It converges. You know what this number over here means? The sample size, the ideal training sample size, the ideal number of samples I need, instances I need to provide, to learn a concept whose shattering coefficient has this behavior. This is very nice. If I plot for the second, what's going to happen in a different color? I don't know. It grows indefinitely. Take a look over here. It grows to infinity. It never converges. Actually, if I plot just this second case here, take a look. It grows to infinite, and it cannot even plot the other values, because what's going to happen with this guy is goes to infinity. So there's no way of representing an upper bound from a probability. If there's no way of representing an upper bound from a probability, there's no way of learning. You know something that's quite interesting? Vopnik, after formalizing this, which is the empirical risk minimization principle, he also proved that the log of my shattering coefficient over n, if the limit of this approaches 0 or is equals to 0, learning is possible. If it doesn't approach 0, learning is just impossible. Learning is gonna never happen. For example, just imagine this. Probably, if you guys remember the paper and pen videos, the last one, you guys saw this term in the generalization bound I showed before. Let's suppose we have a log of 2 power to n divided by n. Say 2 power to n is my shattering coefficient. This is the same as n times the log of 2 divided by n. When I divided n by n, I will have log of 2. Is this equals to 0? No, it's different from 0. Is this going to converge? No. This never converges. Actually, this is a sufficient and necessary condition to ensure that an algorithm learns according to the empirical risk minimization principle, according to this principle over here. Guys, oh, that's a nice example, yeah? I just used like over here, yeah, this is going to be log of 2, of course, but and the limit, this is going to be the same as 1. Very nice. Guys, that's all for now. Hope to see you in the next video. Okay? See you guys.